So we've polished off the convenient criterion. There are some properties of the integral which those of you who want to do a challenge problem, not that everybody's knocking down my doors with doing them, but those of you who wish to can actually prove some of this stuff, but it's all reasonably obvious. If f and g are integrable on R, then so are any constant times f. Agreed? And the sum and moreover you have formulas that if you integrate the constant, I'm going to switch to dv just because it's true in any dimension, then the integral of the constant times the function is obviously the constant pulls out, and the integral of the sum is the sum of the integrals. Does this remind you of something?
Linear map.
Linear map. So integrating over R is a linear map on this vector space of integrable functions. i.e., integrating over R is a linear map from the space of integrable functions to R. That's actually useful to know for purposes not for us right now, but any other properties you can think of? Not so obvious is that if the f and g are integrable that their product would be. Not so obvious.
Why isn't that obvious?
Why is it obvious? I mean, if they're continuous, there's not going to be a problem, as we're going to find out in a few minutes. But if they're weird, it's still true, but it's not as easy to prove as these things are.
What if you had like, I'm just gonna lie, what if you like f was like all irrational numbers in one, and g
It won't
was...
be integrable.
Oh right, yeah, we proved that was an integral. No, I thought we proved it was an integral.
Remember, anytime you do something that's discontinuous on everywhere, it's going to have upper sums up here and lower sums down here.
Right.
Another thing that's worth commenting is if you take your rectangle and you split it in two pieces that don't overlap. So you just split it in two pieces. So if you write R as R prime together with R double prime, and those are overlapping just on an edge like that, what do you think?
The integral over R is the sum of the integrals over the parts.
Right, so then with this picture, f integrable on R, if and only f is integrable on R prime and on R double prime, and the integral is the sum. So this kind of thing we'll actually use occasionally without making a big deal about it. We'll just do it. Or certainly you may well do it in web work without even thinking about it. Okay, so I promised you that we would move forward, and we don't want to go back to the definitions constantly, so the thing I just mentioned is what we want to prove next. So the theorem is, if f is continuous on R, then f is integrable. So this saves you a lot of stress, right? Because if you're in a real life situation, you know you have a continuous function, you don't have to say, oh, I have to prove it's integral, you just know it is. And this is going to be what we do with applications a lot, although we will generalize it later on today or Friday. Any idea how you would try to prove it?
Use
So you want to use the
useful criteria.
Convenient criteria,
Okay, well,
please,
convenient.
get the name right.
Wouldn't you also to assert that R is closed?
R is a rectangle.
Okay.
Our rectangles are closed rectangles,
Okay.
by definition. Okay, so what's the idea? Andy says we want to use the combined convenient criterion, which I'm going to abbreviate. So what do you think you're going to do? So use the definition of continuous. How's that going to help us?
Well, we have like an epsilon delta definition of continuity, so it feels similar. Like
It feels similar, and what's the problem though with the epsilon delta definition? As you move around the set, what can happen with the delta? It can change. So that conceivably, as you get to certain portions of the rectangle, you would have to make tinier and tinier rectangles in your partition to stay within your epsilon changing of the function.
Yeah, we can do that.
Well, what if there's some point where you have to actually make them smaller and smaller and smaller? You're going to tell me that can't happen by continuity. So there's an idea we skipped last semester. And yes, this is one of the things that gets a red mark in Jonathan's notes. So here's a definition and a theorem. Definition. Suppose X is an Rn and F maps X to R. Okay, so I'm not saying it has to be defined on a rectangle, it's true on any general subset that we're talking about. We say F is uniformly continuous
There exists a delta.
Well, before there exists a delta, you need
Yeah, for
So you can pick an epsilon, and then the usual definition of continuity was if you're at a point A, there's a delta. But as you move from different A to different A, the delta changes. What do you think the uniformly means?
the delta.
there's a single delta.
There's a single delta. If for every epsilon there is a delta greater than 0, so that whenever x and y are less than delta apart, and they're both in our set X, we have what?
The difference f of x minus f of y. Magnitude.
Well, okay, mapping to R, so I'm just going to write absolute values.
It's less than
It's less than epsilon. And by the way, this would work mapping to Rm and then putting magnitudes there. It would still work.
So to clarify, we could say there is a single delta greater than 0, or you.
Right? I said there is a delta.
Right, but
than
you're
0.
saying it's the same for every epsilon, right?
No. It's the same for every x and y. The epsilon's given, then you pick the delta that works for that epsilon. I'm not saying the delta works. Be very careful with quantifiers. For every epsilon, there's a delta. When you change epsilon, you change delta. But the crucial thing is that the delta works everywhere.
Okay.
That's what the uniformity means. So in other words, you can set your tolerance level, how much area you're willing to allow, and as you move around no matter where you are in the set, staying in that delta ball, make sure that F doesn't change more than epsilon, no matter where you put your delta ball. And the question is, well, what criterion on X is enough to force that to be true?
Bounded.
Probably bounded. No, we're talking about a set. So certainly you want the function to be continuous. But what must be true about the set, the domain, to make it be uniformly continuous? So think back to basic one-variable calculus. Can you give me an example of a function that is continuous but not uniformly continuous?
The sine of 1 over x thing, right?
Okay. Let's do something a little easier.
Okay.
1 over x. Do you guys think that function is continuous? Yes. Remember, it's not defined in 0, so that's continuous. Do you think it's uniformly continuous? Do you think if I take my epsilon fence that I like to draw and stick it around any place, that I can find a delta that will work everywhere that keeps me within that epsilon fence, no matter where I put the fence? Why not, Aaron? What happens?
You bring it down closer to the y equals 0, then
Bring it up.
Yeah, bringing it down isn't going to be a problem, because as you go out this way, the function's growing very slowly. So actually, your delta gets bigger and bigger out here. Right? If I put my fence down here, there's a huge delta. Where does the delta shrink and get smaller and smaller? As you come in here. Right? As you come in this part of the curve, or this part of the curve, the function's growing faster and faster, so that if you move your epsilon fence up, your delta shrinks smaller and smaller the higher you go. Does that make sense to everybody? Justin?
This is the same thing true for parabola, or?
Okay, what do you want me to do with the parabola? What do you want me to do with the parabola?
I mean, just like the original parabola, just like as you go
So where are you worrying is going to be bad on the parabola?
way.
Up again. So as you go to infinity, as you go out this way, Justin's suggesting that as I go out this way, I have to make the delta smaller and smaller because the function's growing faster and faster. Does that make sense to everybody? If I put my epsilon fence here, I get a delta that works fine. But if I try using that same delta way out here, is it going to work? So if I go way out, I can't even draw it, right? I'm off the board.
Smaller and smaller.
But if I'm out here, the function's gone that much in that little delta amount. It's certainly going out of the epsilon fence that I would move up. So yes, that would also be an example. All right, so what does that suggest you want for criteria on your domain?
Maybe bounded.
Well,
That would solve some of the problems.
but if I
Continue.
look here, yeah, that would solve this problem, Daniel. But if I look here, for that domain, is it solving it?
No.
So, you've all forgotten what was the most important.
Gabe has it.
Well, say it louder, Gabe.
I'm not confident.
So what? Worse than happens is we insult you. Compact, remember, means closed and bounded. So what created the problem there was the fact that you had a hole in your domain, and so you could blow up as you went towards that hole in the domain. Remember, in fact, you had a problem where you made up a continuous function that was unbounded if you were on a non-closed domain?
But we said if you have a continuous function on a compact domain that's bounded, right?
Yes.
Yeah.
And that's the first piece of it. So here's the theorem, and for Jonathan, I remind you. So you have a continuous function on a compact set that's uniformly continuous. And so Gabe's making a point of reminding us that rectangles are closed is going to mean that our rectangles are
Makes sense.
and therefore compact because they're bounded. So this is going to apply to our rectangles, and that's going to make everything work easily. So theorem, if f is continuous, if f mapping x to R is continuous and x is compact, then f is uniformly convergent. So this reminds you, of course, of which theorem that you all committed to memory. Maximum value theorem, right? Similar thing, right? Compact domain, continuous function, guarantees maximum minimum. All right, well, welcome to the new year. It's time to prove this, and then we'll use it to prove the theorem. So let's see. How did the max value theorem proof go? Roughly speaking.
First, we proved that was bounded.
We proved it was bounded. But how did we do that? I mean, just sort of the spirit of the proof. What did we do? We used sequences.
Yeah.
But,
The useful proposition.
yeah, but it was by contrapositive. We did contradiction, contrapositive in there. You could guess we're going to do the same thing here. So we're trying to prove that for every epsilon there's a delta. And we're going to, of course, say, suppose not, and try to construct a sequence that will get us in trouble. Then use the useful proposition again. Ready? So, suppose not. So how do you negate that definition? For every epsilon there's a delta such that. What do I write down? If it's not true,
For some epsilon, there isn't a delta. For a given epsilon, there
okay,
is a delta.
then there is some epsilon naught. So that what happens?
Such that for no delta, that holds.
Okay, can you rephrase?
No matter what delta I choose,
Okay.
there's some like
Wait, slow down. No matter what delta Jonathan chooses. Yes.
there's some I guess x and y's.
Ah, so
X
there
and
is x and y?
There are
Sorry. Some x and y in the set capital X
such that magnitude x minus y is less than delta, and magnitude of x minus f of y is greater than epsilon, or greater than or equal to.
Very good. So what do I do now? If we want to use the useful proposition, what was the game we did last semester? How did we make a sequence out of this?
Take a sequence, pick a set. Pick one of the subsequences.
No, you're ahead of it. How do I create a sequence?
Make a sequence.
Right, for each k, you want something. How do we do something for every integer k? Positive integer k.
Such that x of k is greater than.
But where do we get, I mean, we're going to try to make an x sub k and a y sub k. But how do I get a k in this picture? We used this trick a bunch of times last semester.
Would it go to infinity?
K ultimately will go to infinity.
Or
But
xk?
You don't want x of k greater
No,
than
we
k?
did. F of x is definitely
deltas.
you have to choose a sequence of deltas. How do we do that? The easy way. What did we do for the deltas?
1 over k.
1 over k, right? You want a sequence of deltas that shrink to 0, and for each such delta there's a bad x and a bad y. So for each k in the natural numbers, consider delta equal 1 over k, and then do what Jonathan said. Then for the number delta equals 1 over k, there are x and y. Give them names.
X of k, y sub
X sub k and y sub k. Then for each k, consider delta, you get x sub k and y sub k in our set so that exactly this. distance between xk and yk is less than delta, which is 1 over k, and yet the function values are at least epsilon naught apart. Let me remind you guys, several people caught a typo, a right O in the yesterday's stuff. If you see something, catch me and ask then. Don't wait till after class for us to correct it. Particularly now that I'm being embarrassed in public. All right, what do we do now? Now we do what you guys wanted to do. You got two sequences.
Two convergent subsequences in there. Right.
So let's take one of the sequences by the useful proposition. There is a, okay, so by the useful proposition from last semester. So what did that say, just to remind us?
There's a
Every
sequence
sequence
in a closed set,
In a,
closed compact set,
then
then it has a convergent subset.
it has a convergent subsequence. So every sequence in a compact set has a convergent subsequence. And we also added the remark that the thing the subsequence converged to was in the set because the set's closed. So when you have a convergent subsequence, it's converging to somebody in the set. So we'll need that. So by the useful proposition, we get convergent subsequences for x Now, the trouble is if you just apply the useful proposition to the y's, what might happen?
It's going to eventually converge to x.
Well, I don't know that.
They might not converge.
I mean, yeah, I know what you're
They
thinking,
should both converge to A, right?
but do I know that I'll get the same subscripts when I just abstractly apply the useful proposition to a different sequence y sub k? No. I know nothing, if I just say, let's apply the useful proposition to the x's and the y's, I can't write the same k sub j's. Agreed? So I'm not going to do it with the y's. I'm not going to apply the useful proposition to the y's. I'm going to just stop here and think about what we know now. Okay? So what Dennis said a second ago is right on the money. What does this tell you? Using this and using this, what can you now conclude?
Let's go.
Be careful. Say it carefully. Which y's?
Y sub k converges to A.
No. Which x's do we have control over? The k sub j ones.
Yeah.
So which y's can we therefore correlate with those x's? Yeah, the same subsequence of y's. Right? If you look at the same subscript, what do you know about the distance between the x? Gosh, I want our old room back. What do you know about the distance between the x and the y for the same subscript?
They're going to
Right. Right? It's less than 1 over k sub j, and those are going to infinity, so this is going to 0. So what do you conclude? Louder, Andy? What are these guys are going to what? So here's A, and here are the x subsequents converging to them. And attached to each x, like a dog attached to its owner, is what?
A Y.
A y that's getting less and less far away from its owner, right? So each one of these x's has a y that goes with it. But that distance is shrinking as you go down the subsequence. So what do you think has to be true about the y's? They also have to converge to A. Can you guys prove that? So, ergo, y sub k sub j converges to a as well. Can you actually give me a pedantic proof to make Azov feel better?
It's kind of obvious in the distance between 1 and 0.
What thing that we learned the first week of fall semester might be relevant?
Big limit.
First week,
Squeeze.
trigonal inequality.
Could you squeeze?
No. Squeeze was about functions having limits.
On a separate note, is this the first time we busted out ergo?
I don't know.
Yeah, I think it
I think
is.
it's the second time actually.
Do we make a birthday candle for it? Okay.
Nothing next week.
How do I do this? I look at the distance from the y's to a, and I do that by the triangle inequality, right? Right? You go from the y to the nearby x, and then you go from the x to the a. Well, let's do the step, right? Right, so the distance from the y to the a is at most the distance from y to the x, and then from x to the a. So this is going to 0 because of this. And this is going to 0 because the x sub k sub j's are converging to a. So therefore the y sub k sub j's are also converging to a. Okay. See, stuff like that is a lot easier now, Aaron, isn't it? All right, finish the proof. We're one line from the end.
So, when you know these converge,
We knew both the x's and the y's are going to the same point A. What goes wrong?
that contradicts.
Well, f of a minus f of a.
You're on the right track.
But has to be epsilon not a
There you go.
But it can't be.
Okay, that's exactly what came. So the point is, remember, we had this, which we have not yet called into play. So we have f of x sub k j minus f of y sub k j is at least epsilon naught, but this is going to f of, and this is going to, and the difference is something's wrong, right? By continuity, at A, f of x sub k sub j goes to f of A, f of y sub k sub j goes to f of A. So what does the difference go to? Hard to stay greater than or equal to epsilon naught if you're going to 0. Can we agree that's a contradiction? Okay. Therefore, the suppose not is wrong. Make sense? Why? Want to ask something? Real analysis is weeks and weeks of this kind of stuff. Okay. Do you now believe that? Believe now that we can prove integrability?
That was just a crucial component.
It said it was a crucial component.
I'm so.
Jonathan, don't ever complain your name wasn't in the limelight.
I know for one, so I'm really happy. And it's recorded too, so.
All right, so proof of theorem. We're going to invoke the convenient criterion, we said. So given an epsilon, we want a partition where upper sum minus lower sum is less than epsilon. Given any epsilon, we desire a partition so that upper sum minus lower sum is less than epsilon. How do you think you can use what we just did to try to get that? What did we just prove? We proved that if you pick an epsilon of some sort, if you make points within some delta distance, the function values don't change by more than epsilon.
You just want epsilon greater than a portion or partition of the rectangle.
So how do I want to make a partition here that will make this happen? I'm going to have to pick some sort of epsilon.
Have it be, have it be regular, and then have every little square fit inside a ball with radius delta.
So you don't actually need to have it be regular, but what you do need to know, Daniel's exactly on the right track here, you do need to know that what is true about every little rectangle in our partition.
They're all equal?
No, they don't have to be.
Okay.
But what you need to know, if you're going to try to do a big Mij and a little Mij for this rectangle, what do you want to know to make sure you can control the difference between the sup of the function and the inf of the function?
That the rectangle fits inside a ball of radius delta.
Exactly. All you need to know is that this rectangle has the property that all points in that rectangle are within distance delta of each other, less than delta. So if I take the longest dimension of the rectangle, which I'm going to call the diameter, if all the rectangles have diameter less than delta, choose any partition. Well, okay, I'm going to pull this out of my rear end, and you'll see why I did it. Choose, given this epsilon, choose epsilon prime to be epsilon over the area or volume if you're in higher dimensions of the rectangle. So for this epsilon prime, apply uniform continuity that we just proved. R is compact. And I'm going to use this epsilon, epsilon prime. So there is a delta so that whenever x and y are less than delta apart, f of x minus f of y will be less than epsilon prime apart. Okay, so I'm using the epsilon prime here. And you'll see why. This is one of these things mathematicians do to make everything come out nice at the end. I don't usually do it.
Wait, so R has to be compact.
Yep, but it is.
Wait,
Rectangle, closed, bounded. All our rectangles are closed rectangles.
okay. So we don't need, like, so that's why I didn't say in the theorem. Like, right behind it. Right behind it.
Right. R is a rectangle, which by definition is a closed rectangle.
Okay.
So, choose any partition so that the diameter, so the diameter of a set is just the farthest distance apart 2 points can be. Of every subrectangle is less than delta. So no matter which one of my rectangles I'm looking at, I know that when I compute the big Mij, it's f of some point in there. When I compute the little Mij, it's f of some point in there. And the farthest a point, those can't be even delta apart. They're smaller distance than delta. Note that the capital Mij is f of somebody, and little Mij is f of somebody else. Why is that true? Why is it true that the inf of the function and the sup of the function are actually achieved by taking on values at the points? It's the MaxValue Theorem, right? This subrectangle here is again a compact set, so the function takes its max and its min, so they're actual points where you get them. And so, what do you now conclude? Plug in and you say this. And what do I know about the difference between f here and f here?
Goes to.
No, it doesn't go. So it's an epsilon prime, right? Because these 2 points are in that rectangle and they're less than delta apart. Therefore, by our uniform continuity upshot, this is less than epsilon prime. One line left of the proof, and then you can breathe again. Therefore, upper sum minus lower sum equals the sum of the big Mij's times the area, Rij, minus little Mij times the area. So I'm going to write it this way. This is less than epsilon prime. Oops, wrong epsilon. And now do you see why I made up the epsilon prime that I made up? This is the area of R, and epsilon prime times the area of R is epsilon. That proof really isn't as bad as you thought it was going to be. All right. So that's really nice. So now you know that continuous functions can be integrated. The problem is going to be that in real life, we're not going to be integrating on rectangles very often, especially if you're interested in physics or economics or chemistry or any number of things. You want to integrate over regions that are not just rectangles. You might want to know the mass of a disk. You might want to know the moment of inertia of some cylinder or some sphere or something that's not just a rectangle. So we've got to figure out how we're going to integrate functions over things that aren't rectangles. So I want to be able to take some shape, which I'm fond of calling capital omega, which will be lots of fun for you because in chapter 8 we'll be integrating something called little omega over capital omega, and you'll get all confused. Anyway, don't worry. How do we define the integral of f over a region? some compact set other than a rectangle. So here I have this blob, and I have some function, even that's continuous, say, on that blob. And I want to figure out how to define the integral. So again, for applications, you might want to know the mass. So you might have a density function. Or you might want to know the average distance from a certain point. So you might want to take the distance of a point in this region to a certain point and try to integrate that. There are lots of, starting Friday, we're going to start doing lots of examples with concrete computations. How would I do it? So if I have a function on this blob, this is my omega. How, without starting all over from the beginning, how can I define the integral of f? You could try to divide it into rectangles, but you'll never exactly get there.
Well, you could take the limit
Of trying to exhaust it by the tinier and tinier
Yeah.
rectangle. Oh gosh. I really don't want to do that.
Could we do something like, take a distance from the edge, like a strip around it, and do multiple strips till you get to the center?
No, but I still want to try to define the integral just using what we've already done without starting and inventing things from scratch.
Put a rectangle around it?
Put a rectangle around it. You're not quite out of the woods yet.
How's that different or better than putting rectangles inside?
Ah, this is way easier, you'll see.
Okay.
So why do I know I can put it inside a rectangle, Jackson?
Because it's compact.
Because it's compact. So it fits inside a ball, and the ball fits inside a rectangle. All right? So here now, choose a rectangle, R, with omega contained inside R. Well, wait, my function is only defined on omega. How am I going to just... I don't know what to do yet. Either you guys have been doing your reading, or else you're being really good. I'll choose to believe that you're doing both. We're going to define a function by define f bar, which is going to be on the rectangle, by just saying do f when f makes sense, and make it be 0 everywhere outside.
But then will f be continuous?
Of course not. I'm so glad you asked that question. So,
Would you like the properties of integrals?
define, not quite. Define f bar by f bar of x is, sorry I'm stuck in the corner here, is f of x when x is an omega and 0 outside. And then say, set the integral of f over omega to be the integral of f bar over the rectangle. So the ultimate question is, what hypothesis do I need on f to say that this guy will be integrable? Provided f bar is integrable. So as Daniel's pointing out, if, for example, I had a function that was like, say, positive on omega, something like a density function, then the rectangle would now have a density function that looked like the original one here and 0 everyone here. So it's like making this rectangular mass where there's no mass outside here. It's just infinitesimally light plastic, and all the real mass is concentrated in here. But how do I know I can actually integrate?
They would do the property that's like if you add two together.
Yeah, but that was only for rectangles.
It's not,
It was not for weird shapes, right?
Oh, really? Oh.
Not like f bar, it's like bigger than f,
Well, this f bar is defined everywhere, but it's 0 wherever f wasn't defined. So they have different domains.
What do we try to do? Why do we have like?
Say louder.
Why do we have provided f bar is integral?
Well, because otherwise, if this isn't integrable, this doesn't make sense.
Okay.
So I'm going to say f is integrable on omega when f bar, as we've just defined it, is an integral function on the rectangle.
Well, when wouldn't f bar be integrable?
If f were really bad to start with,
Okay.
So if F is,
right? If f were really crazy discontinuous, then there's no hope for f bar.
Okay.
but if F is integrable,
Well, I don't know what that means.
oh yeah.
How about f is integrable on every rectangle inside omega? Could we go
You
that
mean
way?
every, that's a great question. You would not necessarily make this be integrable, because the frontier of omega could be super messed up.
Okay.
So you want some sort of reasonable omega, and then you want some sort of reasonable f.
So omega compact.
Omega is compact.
How about the boundary of omega is a manifold or something like
That would be fine, but in fact, a lot of our applications, it won't be. It will have corners.
that?
Right? If you just want to integrate, as we will on Friday, over a triangle, this is not a manifold.
Right.
But it's close. It's just got corners. All right, so I'm going to give you the punchline, and then we'll pick up with this Friday, and then we're going to start actually trying to compute things. So here's the punchline. And I might actually talk a little bit about this proof on Friday. So here's a definition. I'm running out of time, but I'm going to try to say this quickly, and then we'll do more on Friday. So you say X has volume 0 in Rn if you can cover it up with finitely many rectangles of arbitrarily small volume. So a subset X like this, you could cover it up with rectangles and make the sum of the areas of those rectangles as small as you want. You can do a very small job. If for every epsilon there are finitely many rectangles, which may depend on epsilon, of course. So finitely many rectangles R1 to Rs, so that X is contained in their union, so they cover up X, and the sum of their volumes is less than epsilon. So that set X is sort of a thin set. It has no area, it has no volume in the dimension 1. Here's the ultimate theorem. If F mapping R to R is continuous except on a set of volume 0. Then, what do you want to guess?
Integrable.
So, what do I want to have be true about my omega?
It's frontier boundary has one.
Corollary, if F mapping omega is continuous, and the frontier of omega, that's the points where the F bar is going to be continuous, has volume 0, then you start with continuous function on omega, it will be integrable. Then F is integrable. And so we're going to call omegas that have this property omega compact, and with this property is called a region, and that's what we're going to deal with.
When would the frontier of a set not have volume?
You can have really wild, crazy, space-filling curves as boundaries of a region in the plane. Okay, I ran over a little, I apologize. You guys don't normally have office hours on Wednesday, but I have office hours, I think it's 1:30 to 3 for the other class. So